here as an integration constant connect with the, let's say, Bianchi identity, okay? So the status here is very different because now it's something that was not in the theory and appears at the integration constant and mass observation will say the values of this. So a new status for this, and I go to develop this later. However, how can we are obliged really to impose the conservation of the energy moment tensor? Not appear, not all right. Okay. Well, the point is that if you perform a diffeomorphism, in order to preserve the unimodular constraint that G is a constant, we must, in opposition what happens in general relativity, we must, this parameter here is not arbitrary, but must obey this, this condition. This is in order to preserve the unimodular constraint. And so the unimodular theory is invariant not by diffeomorphism in general, but by a restricted class of diffeomorphism that we call transverse diffeomorphism due to this condition here. And this has a lot of consequences, okay? For example, let's vary the action, general relativity, with respect to this parameter, diffeomorphism, obtain this expression. Okay, it's direct to see this. Just interpret Gemini as the covariant derivative of nu. Okay, and make integration by part. This term goes out because of Bianchi identity, and this we have this that the divergence of the energy moment tensor must be zero. So in general relativity, the conservation of energy moment tensor is a consequence of the diffeomorphism. In unimodular gravity, due to the transverse diffeomorphism, it's different because in doing this computation, we arrived here, okay? We can make integration by parts. General relativity is okay. This must be zero for an arbitrary vector. But here, in unimodular case, general relativity is this, but in unimodular case, I can suppose that the divergence of energy moment tensor is the gradient of scalar function, some scalar function. So we obtain this, if I replace here, and make another integration by part, you obtain this, and this is zero in order to preserve the unimodular condition. So, in general, in unimodular gravity, we do not have the obligation to impose zero. We can, but cannot. It's enough to consider this phi as a constant. Okay, or zero. But it's not. You can consider more general case, and but this, in principle, this function here phi remains unknown. But we can make some choice. Okay. So we can we have seen that if the energy moment tensor is satisfied, we end up with general relativity cosmological constant. And if we do not consider that the energy moment tensor is conserved, we can return back to this equation. Okay, call now for convenience the divergence of energy moment tensor as this expression here, returning to the equations I have. What I obtain now is this relation here. Okay, it's natural. I have called phi of lambda. And going back, I obtain again general relative equations, but general relative equations with a dynamic cosmological term. Okay, that is very common, interacting model. In fact, there should be a minus here, okay? Sorry. So what if the usual conservation law is not obtained? What we have is just general relativity with a decaying vacuum. So it's not a very unfamiliar also. So only in general relativity, by the way, you face the same problem because in general relativity, when you have a decaying vacuum, you must impose somehow how does vacuum decay. What is a good thing in order to explain, by the way, the small value observed today of the cosmological constant. But here comes from the conservation, it's natural. If I have lambda constant, okay, I come back to general relativity with a cosmological constant as usual. But we can have a more general structure. That's not, I stress this, it's not unknown in general relativity. There is a lot of models of decaying vacuum general relativity. So are completely equivalent, both formulation, more or less, because I will give an example considering a specific case. Let's take a freedom model with a hole and using let me say, should have put again the relation, this relation here. Let's return to just the structure, that the original structure of unimodular gravity. And when we do this, okay, in the freedom model, for example, flat, just to simplicity, you obtain these two equations. This first one comes from the gravitational equation. This comes from the conservation order, the new expression for the conservation with these different terms. And of course, we say I have two variables, who and age, p I can choose, and I can just solve this. But it's not the case, because if you look better, if you insert this first equation here in the second, you obtain 0 equals 0. So the second equation gives no information at all. What is not, it's not surprising, because since the non-conservation of energy moment tensor maps unimodular gravity in an interacting model in general relativity, you must suppose something else in general relativity. You must suppose the form that the vacuum decay. Okay, and here you must also add an ansatz. We have made an ansatz. Suppose that the fluid would becomes behave as a radiation fluid, and this amounts to consider the interacting term as with this form, H F times rho, which is the matter. So we have this interaction. Now, and the solution, it's simple. It's like, in general relativity, a radiative universe with a cosmological constant. And the solution are like this. The Hubble function is given in terms of the cotangent parabolic. Here appears the lambda that we add index U just to indicate that a lambda comes from a constant that comes from the unimodular structure. Okay, not from Lovelock or the thing. And we have also an expression, of course, for the deceleration parameter. We have shown that this may lead to a universe at least where age compatible with observations. Okay. This, of course, we could expect since the result of Lemaitre. The addition, something that plays the role of cosmological constant, may becomes the universe quite old, as we observe. But the problem is that in this case, we have just formation of structures. We have just radiation, sorry. And we know that in the standard model that a radiative universe cannot form structures because of gene length. The pressure is very big, any perturbation will oscillate, not agglomerate. Mass, for example, the standard model will wait for the matter-dominated phase in order to have the agglomeration of matter. Okay, and in this case, since I have everything like general relativity with an interaction there, should expect more or less the same. Okay, but not exactly, because the problem that it cannot use in principle. There is discussion of this in literature. Okay, now, but as the most common point of view is that we cannot use all the variables, perturbative variables, as you use in general relativity because of the unimodular constraint. You must obey every time that the determinant of the metric must be fixed. So the perturbation also. We can simplify the following. Is that in general relativity, with just matter, we have, for example, this equation that connect the perturbations of the metric here, H, that I call H, and the perturbation of matter. Okay. We can solve this equation, combine with the other one. But for example, I just consider this to illustrate what I have in mind. However, due to the transverse unimodular condition, this quantity here is zero. And if this quantity H here is zero, insert here, you obtain delta rho is equal to zero. So no perturbation at all. It means there is no perturbation? No, it means that the use of this coordinate condition is not appropriate for unimodular case due to the diffeomorphism. And what we have done, when there is 2 points here. First is that when the energy moment tension sorry, I have not put here one important here. It's a remark here. The point is that if we impose the conservation of the energy moment tension, the usual one at least, in the due to the modular condition, only the gauge invariant formalism can be used. It means that the synchronous gauge that leads to this expression, or the Newtonian gauge, okay, that leads to equivalent expression, cannot be used. Okay, but when the energy moment tension does not conserve separately, we have in mind as here an interactive model, so we can use both the synchronous gauge and the gauge invariant formalism. The Newtonian gauge remains forbidden in some sense. That means that lead to no information at all, between 0 equals 0 everywhere. And for simplicity, we have considered synchronous gauge. And when H is 0, but there are other quantities. Okay, and the other quantities, for example, you have this quantity that's not 0, and looking for not show here the perturbations or all the perturbation analysis, but when we develop these structures, okay, what you have, all the perturbed equations, we end up with just one equation for this variable f. Let's connect here with this divergence of the HEG, the perturbation. And this equation, what is very remarkable here is that we have, in principle, like in general relativity, damped harmonic oscillator, in principle, damped because there is the friction term, but with the wrong sign. It means it's a damped anti-harmonic oscillator. This minus appears also when considered gauge invariant formalism here. And the result, we are in the radiative phase. The result is that the solution is given by hyperbolic function instead of trigonometric function. And this, of course, shows a huge increase in the perturbations. So even if you are the radiative case, due to the structure of the theory and the imposition of the unimodular condition, okay, we have a complete different background would be the same as general relativity interacting model with a decaying vacuum. But at perturbative level, it will be completely different. And this perturbation is still very, very dangerous even because it becomes perhaps unstable. But we cannot say this at this moment because we are at linear level. In order to be to verify the instability, must go to the second order to verify if when we go out from the linear regimes. No, no. Suppose. I suppose, but we must verify at linear level if the non-linearity can stop this growth. This is the point. We are investigating this point now. Okay, we have not an answer, but it's important to stress this. Okay, but in principle, it should be a controlled growth of the perturbations. Okay, but this shows disappointing that must also be honest, that's confess that it's a point on discussion literature, to which point, in fact, unimodular goes back to general relativity. Our argument, based on this result and other results we have obtained, is that at the background is the same general relativity, either with a cosmological constant or with a decaying cosmological term, okay, a dynamical vacuum, let's say, in this language. But at perturbative level, it has many new features, okay? But there are other point of views, okay, about this. And let's look now to this static spherical symmetric case. Okay, we see what's the main difference. In there, when analyze this problem, we can give some example of why, in fact, the unimodular gives a new view of the cosmological constant problem. Here, it's important, of course, because stars, it applies this problem, spherical symmetric case, apply to star, black holes, everything, but because it has less symmetry than the Friedmann model. Okay, so we can perhaps see if the result we have obtained has something to do with a very symmetric state. So let's consider a static spherical symmetric solution with three coefficients, gamma, alpha, and beta, that are function only of the radial coordinate. Of course, I use here the radial coordinate as u, just to stress that perhaps not to do is direct with the radius air that you actuate, and that's our radial coordinate. But we can reparameterize this radial coordinate, so these three functions are not independent. We have two only, as usual. General relativity the same. Okay, and let's see first what happens when I have electromagnetic field. In this electromagnetic field, the trace of the energy moment tensor is zero. So the equations comes from this situation, and that modified conservation law reduces to this expression. If I impose the Maxwell equations, okay, this must be zero, I obtain, again, a return back to the structure typical Heisenberg solution, okay? But if I do not impose, because I'm not obliged in the case of unimodular, okay, I have some new features. But first of all, let's specify that I consider, since I'm taking the static spherical symmetric, I take the only non-zero component of the energy moment tensor, F01, that is the electric field, just for simplicity. So I have just one equation. If I do not impose the validity of the Maxwell equations in these structures, okay? The sense that I will keep this structure, air not necessarily a constant, that as is happening in Heisenberg. So I have just one equation that have these two variables, okay? And now, since I can use any coordinate system, radial coordinate system, I can fix the class global coordinates since alpha minus gamma, this is a choice. That, by the way, has not satisfied this condition, and obtain that beta from here satisfy this usual expression. I come back in principle to Heisenberg solution. But I remarked that that modified conservation law leads to this expression. If lambda, that lambda here, I call lambda, in fact, the air over 4, okay? If lambda is constant, we have the usual behavior for the electric field, and we find again the Heisenberg solution with a cosmological constant. But if lambda is not constant, it is allowed in the unimodular structure, I can have a more complicated structure. For example, for the lambda constant, we have this, okay? Heisenberg with a cosmological constant, okay, and the electric field. But for the lambda, not constant, sorry, just a point, I must impose some condition on lambda. And depending on lambda, what we impose, we obtain new terms in the solution here. Connect with the variation of the cosmological term. However, this new term, for example, cannot address the problem of the singularity, because add new term, but this term we present like as solution of the homogeneous equation. So the solution will be more complicated. We can have different structures, in general, two horizons as Heisenberg, but you can have also negative singularity, different from Heisenberg, wormholes, a lot of new structure, depends on how you put as the decaying vacuum term. Okay. So this is structure. But let's go back now to the scalar field. The problem of static spherical solution with a scalar field. And add here epsilon in order that can be positive or negative depending if you have ordinary scalar field or a phantom scalar field with negative energy. Okay. And look that here I choose the energy moment tensor with self-interacting potential. That cosmological constant can be obtained, or the vacuum term as a particular case, but it's enough to put phi as a constant. So V will become the cosmological constant if the scalar field is a constant. Okay. But in modular gravity, this is the new equations. And see one aspect that the potential self-interactive potential has appeared. No trace of it. Like the cosmological constant, if you put in the original action, it disappears also. So this is the main point of the modular, that in some sense is the idea of the gravitation, but in a very crude way. It means that even if I begin with a cosmological term, if you can interpret, for example, as vacuum energy term, it disappears from the structures. So I have this very complicated equation. So I think I ran out of time. Okay, better finish. Okay, but I have to impose one condition to solve this equation. This is not, again, I stress, not a problem, because to impose a condition means corresponding general relativity to impose a behavior for the decaying vacuum. That must also impose. So we have the same status in some sense. And the conservation law takes this form. If now I say that this obeys the Klein-Gordon equation, the scalar field, okay, we can integrate, if it disobeys the Klein-Gordon equation, this becomes 0. I can integrate this, it will appear, okay, not 0, it becomes the derivative of the potential, Klein-Gordon equation, remember, okay? But here, this term is just derivative of the potential in the end, and you can integrate leading to this term here, and everything, not again, general relativity with the potential term that appears from the Klein-Gordon, because I have imposed this, and the cosmological term, and we obtain everything again. However, okay, if now if I do not impose, I end up just with just two equations. There are only equations I have if I do not impose the Klein-Gordon equation, that is the conservation of energy moment tensor. And I have to add some behavior, some ansatz. And this ansatz mounts, it's equivalent to choose a potential in the general relative case. Here it's an ansatz that I make on the scalar field, okay? For example, using general relativity, we have determined, by Nelson, Kirill, and Manuel a long time ago, the solutions, okay, without potential, okay? And it was in general relativity with phi, p, okay? And we have this structure that belongs to the class of called the cold black holes, okay, with this constant obeying here, this parameter A, obeying this condition with a scalar charge that's connected with C, here it appears. And it's easy to see, but we must make some calculation, that black holes can exist only for the phantom case that correspond to epsilon equal to -1. And this solution obtained with zero potential and represent a black hole only for -1. And the same it appears there. You can put there it will be solution of the unimodular, and we would have no potential at all. But in unimodular case, we must suppose the behavior not of the potential, but of the scalar field. Okay, that's the difference. And the same happens for a regular black hole that I determined with Kirill-Bronikov a long time ago, that have a very complicated behavior for the scalar field and a very complicated potential. So in unimodular case, there is no potential. But if we impose this condition, it satisfies the unimodular equation also. Okay, but must impose. Here we found this by supposing this potential. That's quite complicated, but it was made ad hoc in order to obtain regular black holes. Okay, and we can have, just to finish it, two aspects of the problem. First of all, okay, we can have the same solution in the modular case and general relativity, but the procedure of what we are supposing is different. In general relativity, it's the form of the potential. In unimodular case, is the form of the scalar field only. There is no potential at all. Okay, appears nothing, but we must suppose something. And we can ask, and for example, the Birkhoff theorem is valid. It's different in one case. No, because we can take the 0-1 equation of the gravitational equation, component of the gravitational equation, it reads like this. Okay, and in general relativity, what's happened is that if you use this choice for beta that is allowed, okay, the theorem is verified because this becomes 0, this becomes 0. If this term is also 0, that is, if the scalar field is static. So we recover the Birkhoff theorem, but it's the scalar field is dynamical. The Birkhoff theorem is violated due to this term here. This is shown, for example, in Weinberg book when analyzed the Birkhoff theorem, how to proceed. The same thing, and in unimodular gravity, we have exactly the same behavior. Okay, and Birkhoff theorem is valid or not depending if the scalar field is dynamic or static. Okay. And finally, there is a point. In general relativity, that solution I have shown for the scalar field with scalar charge is unstable. Okay, when we make for small perturbations, we have made this twice. Using a gauge, we have found that it's stable, but when using the gauge equivalent of gauge variant perturbations, we have found the instability. The choice of the gauge was hidden somehow the unstable mode. But here in modular context, the problem is not defined because we have the from the modular condition this relation, and we can always use the quasi-global coordinate and keep this condition at perturbative level, delta alpha plus delta gamma equal 0. Okay, and we end with delta from the unimodular condition, we end with delta beta equals 0. So there is no perturbation at all. And this is somehow disturbing here, because remember what happens in cosmology. There was some problem of the gauge, because in general relativity, the choice delta beta equals 0 corresponds to choose gauge invariant formalism. So again, it seems that new features appear at perturbative level due to the restriction to transverse diffusion. So just to remark is that unimodular gravity reduced to general relativity with a cosmological constant when the energy moment tensor is imposed. If it's not imposed, we have essentially to evacuate the decay mode. I have not quoted this, but in fact, there is a de Sitter background I have not discussed here, should have discussed, okay? And so we have the map. Unimodular can be mapped either in a general relativity cosmological term or in a general relative with decay mode. But for the backgrounds, when you go to perturbative level, new feature appears, and apparently the results are very different when, for example, for the formation of the structure and for the stability of black holes. Must just for the final remark say, okay, it appears just new features that I have shown when imposed do not impose the conservation of energy moment tensor, but Brandenberg, Kai, I don't remember who more, okay, a paper some years ago had analyzed with the conservation of energy moment tensor using the gauge invariant formalism, even though they have shown a new mode that appears at unimodular case. So perhaps there is an equivalence of the theory at the perturbative case, what is not perhaps bad, due to the many problems we have general relativity with this. For example, we need the dark sector. There are many problems that can be traced to this. So perhaps the unimodular can, at the same time, address the problem of dark energy and dark sector. But we must first understand better what's happening at perturbative level. Okay, thank you.
Okay, questions?
Thank you, Professor. You talked about the black hole instability problem. You said that Birkhoff theorem is only obeyed if the field is static, if the scalar field is static, right? So it doesn't make sense to think if no Hare theorems apply here.
Well, the problem is that depends on the matter content. For electromagnetic field, the Birkhoff theorem is satisfied, no problem. Even unimodular or general relative, okay. When scalar field, it's natural somehow to expect that Birkhoff will not be satisfied if the scalar field is dynamic, because we have a monopolar emission, gravitational wave, okay? And when Birkhoff means radial oscillations, okay? So concerning the Hare, the Hare would be, I think, another question, because it's a problem if the black hole should be characterized by other parameters besides rotation, mass, and charge.
So,
and for Hare, if a scalar field is added, it's possible to have a Hare.
okay.
Not necessary. There is a work by Carlos Herdeiro from the group of Portugal that discussed this very in detail, that we have Hare, for example, in a Kerr black hole, if you surround it by a cloud of a scalar field or something.
Okay.
But as far as I know, there had not a direct connection with.
And has someone calculated black hole shadows of this theory? Do you know about it?
The shadows has been calculated for many of this. I do not know if it has been calculated for Heisenberg with a cosmological constant. Static, but must put a rotation, perhaps, or perhaps not. For the dynamic scalar field, no, I think not, because for dynamic scalar field, we go out of the static case. And I think you must, I do not know if there exists a close background solution even, okay, for description of black holes. For static case, it exists. Unfortunately, always unstable, but it exists. Solution to this.
Okay, thank you for the talk, Julio. Here, this part about the structure formation, even in the absence of dark matter, it sounds like a good feature, but it could be a bug. What does the dark matter do to does it enhance the structure formation? Does it hinder the structure formation? How does it affect?
You are mean, for example, dynamics of galaxies.
That's correct. So it looks like you can produce structures even in the absence of dark matter, right? At least that's what the sentence means. So now that we have add dark matter, does it enhances the perturbations, and does you have structure formation happening sooner than later?
I don't know if this is very well, because what I mean is that why need, there's many aspects of dark matter, because dark matter appears, for example, in dynamic of galaxies, dynamic of cluster of galaxies. Okay, this must be explained perhaps for another mechanism. For example, perhaps correction to Newtonian potential. Okay, this must be investigated in this case. However, the structure formation, what you need the dark matter, because you need to agglomerate something in order to create the potentials, okay, during the radiative phase. Here, it's not necessary because already, if baryonic matter, if they are subdominant, or even the radiative fluid will agglomerate, okay? So in this sense only that I have.
Possibly there will be some constraints coming from the observations on the theory from this part.
Yes, must be constrained. We have not exploited, we have only look at some more direct constraint, because it's quite recent to have done all this. The concern, for example, the age of the universe is some aspect of this. It's okay. But the detail of the formation must be investigated better, mainly because there's this amplification of the perturbation is very huge, exponential. So you must look out at nonlinear regime if it's okay. That's I think the first step after these results.
Sure. The second thing is, see, the Birkhoff theorem originally by George Birkhoff, and the one presented in Weinberg's book and elsewhere is as a vacuum solution. So you have the scalar field. You are talking about the Birkhoff theorem in the context of scalar field. So maybe you mean spherically symmetric static, may not mean Birkhoff, do you?
Well, Birkhoff is, in general, Birkhoff is in vacuum, general relative, okay. But when you add matter, this is a problem to say. Any radial oscillation of the star will be felt outside the star. In other words, there will be an emission of monopolar scalar radiation besides gravitational radiation. Okay, there's a problem, and you can think this in any structure.
That's correct. So Birkhoff theorem perfectly eliminates that possibility. There is no zero mode. There is no zero mode of gravitation. Right?
Yes, but this requires for a scalar field, the scalar field is static.
Sure.
Okay, that's a.
We'll talk to you later.
Okay. What's very restricted for a dynamic situation.
Okay, so thank you, Jules, again.
Okay, thank you. Okay.
Okay, so let me invite Professor Bourgeois to talk about quasi-classical description of quantum effects in cosmology. Thank you. Have an hour.
Thank you. Thank you for the invitation and the introduction. Quasi-classical effects or descriptions is a pretty broad topic, so I'll focus here on one issue which is often ignored but probably relevant in cosmology, and that's non-locality. So usually what we use as effective actions follows particle physics ideas, low energy effective actions, and they are obtained from derivative expansions. Just to simplify things, because fully non-local actions would be too complicated, we know that the full quantum effective action is non-local. So it's, for instance, based on path integrals, it sums over all trajectories which run everywhere in space or everywhere through time. And if we have a full action principle for quantum effects, it has to be non-local. Derivative expansions make it easier, and because it's in space-time, it also includes an adiabatic expansion. So these approximations, again, particle physics, there's usually no problem. But in cosmology, large-scale effects or early universe large curvature mean that we have non-locality. We probably have non-adiabatic effects too if it's high curvature and things are changing very rapidly. So they might be important. Now, it turns out other areas like quantum chemistry have been looking for quantum approximations that can describe non-adiabatic effects. Chemical reactions happen very quickly. So they have to get good approximations. And they can be extended to a canonical version of effective theory, which includes non-locality, which can be extended to space-time, still being worked out, but at least in principle, that's possible. So I'll describe this a little bit here and present a few examples. Tunneling, multi-field inflation from single-field model. So that's there's some early universe effects in there. Inflation is low rho, so it's very adiabatic. But the beginning and the end of inflation, so starting it off with the right initial conditions, getting a good exit, can be improved by non-adiabatic effects. And if I have time, I'll talk a little bit about non-local effects in back reaction for structure formation. So how inhomogeneity can be created from a vacuum state. So first, quasi-classical descriptions, there are different ones. So what I'm using here is based on a reformulation of quantum dynamics. And a simple example, just to get an idea, is based on the uncertainty relation. So we can describe some quantum effects just focusing on fluctuations. And fluctuations are not arbitrary. So there are two fluctuation parameters, and together with a covariance, CXP, they form a certain manifold. There are uncertainty relations which imply boundaries. And in quantum mechanics, that boundary is different from classical mechanics for space-based distributions. So that's an example, simple example of the kind of quasi-classical methods that I'll be using. And we can already see here, it's a three-dimensional phase space. It's odd-dimensional, so it can't be symplectic. Instead, we'll have to use Poisson geometry. And that turns out to have a nice relationship with gravitational descriptions, canonical gravity, for instance. Then the dynamics, so that's a version of a standard quantum mechanics description, dynamical. So in this case, time derivatives of the expectation values determined by the commutator with the Hamiltonian. And we can reformulate this without any approximation at this point by viewing the, or first defining an effective Hamiltonian just as the expectation value in an arbitrary state. So we assume that the Hamiltonian is given for a given system, then this defines a function on state space. It could be pure or mixed. So it's like a Hamilton function, classical type, but on an infinite dimensional phase space, the state space here, on which we'll have to introduce a Poisson bracket. And this can be done like this. So very natural definition. The commutator obeys the Jacobi identity, which is also an important condition for a Poisson bracket. So that's a valid definition. And then in general, we might have to include products of expectation values, as in the variances, for instance, and then we just impose the Leibniz rule, product rule, to determine the Poisson bracket of products of expectation values. So that's a good definition of a Poisson bracket for functions on state space. So again, on this infinite dimensional phase space. And then with these two definitions, the equation up here is just like a standard Hamiltonian dynamics equation. Time derivatives of functions on phase space are determined by Poisson brackets with this effective Hamiltonian. So again, no approximation, but it's infinite dimensional, and usually if complicated Hamiltonians couple infinitely many different expectation values. So we do need approximations, and that usually starts with a truncation. So we'll try to focus on at least a finite number of relevant observables and expectation values. And then we try to make sure that equations of motion are also truncated so they don't couple to anything else. So that's an approximation in which we assume that these coupling terms are sufficiently small. A large class of examples is a semi-classical approximation. So we fix some integer n, and that's going to be our order in h bar. We can use suitable expectation values. So the basic ones of if we have position momentum or configuration momentum variables, then if they're canonical, then the Poisson bracket on the previous slide implies it has a standard type Poisson bracket. So it's still canonical. And everything beyond that, that's not just simple expectation values. Basic operators can be expressed in terms of central moments defined here in completely symmetric ordering. So this can be defined, of course, for any a plus b, but then the truncation happens if we restrict this to a set where a plus b is no larger than 2n. So that's an expansion to in h bar of order n. So it translates to 2n for moments. Now, the effective Hamiltonian, initially on this infinite dimensional phase space, it can first be expressed in terms of moments by this formal Taylor expansion. So we, in first line, just the definition. And then in the expectation values applied to Q and P operator, so we just write these as expectation values plus operator minus expectation value, and then Taylor expand in these differences. So the result is a function of moments and basic expectation values. The leading order is just the classical Hamiltonian. And then there are moment terms which have coefficients defined by derivatives of the classical Hamiltonian. So that assumes a specific ordering because the moments assumed completely symmetric ordering. The Hamiltonian has to use the same ordering. Otherwise, there will be reordering terms which depend explicitly on h bar. But that can always be done if such an ordering is preferred. If the Hamilton operator is a polynomial, then it's a finite sum. So it really just rewrites the initial function as a function of these central moments. If the Hamiltonian is not polynomial, as usual in quantum mechanics with these approximations, it's an asymptotic series. So it's not convergent, but one can still make sense of it. Well, I start with the Hamilton operator. So your quantum system defines. Well, it's defined. No, it's defined by this equation. So for any state, the effective Hamiltonian takes a value which is equal to the expectation value of the Hamilton operator in the same state. Well, it does according to this equivalence here. So these two equations imply that the first equation, which is standard quantum mechanics, is completely equivalent to the bottom equation. So it is the time generator in this phase space on the state space, which is turned into a phase space with this effective Hamiltonian. So it's really just rewriting. At this point, it is standard quantum mechanics. The effective Hamiltonian is completely equivalent to the Hamilton operator. And we start making approximations when we do these truncations. Because usually it's a function on an infinite dimensional space. So it's Hamiltonian dynamics on an infinite dimensional space, which we try to simplify. And that's done by this truncation first. So it restricts your state space, phase space to a finite dimensional subset. And then we have we use variables. So instead of using density matrices to label points in state space, we use moments and expectation values. And we re-express the original Hamilton function in terms of these variables. So again, just a reformulation. And then the approximation happens if that's really an asymptotic series or a long sum, and we want to truncate this to a shorter expression. But again, completely, without these approximations, it would be completely equivalent to standard quantum mechanics. And no new ingredients, so just reformulations. And then the final point here, it's a series in moments. And for semi-classical states, it's a series in h-bar. There are some states, lots of states, in which moments are not analytic in h-bar, so we can't always translate this into an h-bar series. But for semi-classical states, that's possible. So it's an h-bar expansion in this case. Now, some properties of these central moments, by definition, they are real. They are expectation values of symmetrically ordered expressions. For semi-classical states, they obey this hierarchy. So higher orders of moments correspond to higher orders, higher powers of h-bar. And of course, that's what Gaussian states do. But Gaussians are really just one example. It's an infinite dimensional set. If we truncate to order n, it's a set of dimension, I think, n times n plus 1 over 2 or something. Gaussians are just two-dimensional. So that's only really one small subset of this whole moment space, even if we impose this semi-classical behavior on the moments. They're Poisson orthogonal. One can show this. That's a little more tricky than just the QP identity, but each moment has vanishing Poisson brackets with the Q and P expectation values. But then, unfortunately, the bracket of two moments is very complicated. So it's a long series expression here. It's not linear. There are quadratic terms in some of the brackets. And they're certainly not canonical in any obvious way. So there are no constants on the right and no zeros usually. And this can be a problem. So first example will just be the free particle, just to see how this works. In this case, so we know this Hamilton operator. And then the effective Hamiltonian is just the expectation value. So we just rewrite the square of the operator as the square of the expectation value plus the variance. Again, that's an identity. In this case, there's no truncation because it's a simple system. But the question is then, in this mechanical or Hamiltonian dynamics interpretation, is this delta p squared over 2m another kinetic energy, or is it a potential energy? Delta p here, it's now a two-dimensional momentum, or let's say a five-dimensional phase space. So we have qp, only p appears in the Hamiltonian, and then we have delta q, delta p, and cxp, the covariance. So it's a five-dimensional phase space instead of just two in classical mechanics, so independent degrees of freedom. And for interpretations or evaluations, we want to know whether this new term is a kinetic potential energy or maybe both, when it can be split up into two terms. And now in this case, it turns out it can be answered quite easily. There's this Darboux theorem, or Casimir-Darboux, an extension to Poisson manifolds, which shows that locally on any Poisson manifold, so anything that has a Poisson bracket, we can always find coordinates which are canonical. So Q and a P, which have, or a set of Q's and P's, which have delta ij Poisson brackets. And then because it's Poisson, not guaranteed to be even dimensional, in general, there are also these Casimir functions which have vanishing Poisson brackets with any other phase-space function. So these would be conserved quantities independently of the dynamics, just based on the Poisson structure. So they exist locally. And also here, it's not so easy usually to apply this theorem because it's not constructive. It only shows the existence. But in this case, there's a simple solution. So here are the three relevant non-zero Poisson brackets of second-order moments. So we can work that out using the previous definitions. And the next line here defines a canonical description. So basically an application of the Casimir-Darboux theorem. SPS are the canonical pair, and then there's one C that commutes with everything else. S is just the quantum fluctuation here. PS appears in the covariance, and then C in the momentum fluctuation. It's important to include the C term because if we don't, we violate the uncertainty relation. So the left-hand side of the uncertainty relation is just this combination here. If C is equal to 0, that would be equal to 0, but it has to be greater than or equal to h bar over 2. So, so we really need all three dimensions. We need S and PS for the canonical variables, and then C, still a free parameter. It could be greater than h bar squared over 4, but we need it to respect the uncertainty relation. So that's been known for some time, not necessarily in this Poisson form, but it appeared as an example, a model of quantum field theory some time ago, first time probably. Then in an analysis of quantum chaos, quantum chemistry, so that's where this approach started in for non-adiabatic reaction dynamics. And then more recently, also in cosmology. So now we can complete the free particle. So we have this expression for delta p squared. And now we see it's a combination of kinetic and potential energies. So it's kinetic through this PS, the new momentum, and then this uncertainty term defines a repulsive potential. Even though it's a free particle, there's a potential in this fluctuation direction because uncertainty relations have to prevent it from reaching 0. So there's a potential, but it looks just like a centrifugal potential. So if we go to an extra arbitrary dimension, we can write this as the centrifugal potential in this XY space. So S would just be the radial coordinate in this space. And phi is an angle which is not physical. Just introduce it to rewrite the dynamics. Then in this extended space, it's again a free Hamiltonian, just kinetic energy. So we have straight lines as solutions in this XY space. And XY don't couple to Q, so we can separate this dynamics. It's rotationally symmetric because this angle phi doesn't matter, so we can always align the trajectory of the x-axis. And then we can easily find the solution just from geometry here. So S, again, is the radial coordinate, so it's the distance from the origin to this moving point in this fluctuation space. And the impact parameter, as always, is angular momentum over linear momentum. This distance here is velocity or times t or pt over m. And then in this right angle triangle, we get S of t with this dependence, which of course is just what it has to be for quantum mechanics. So in this case, again, everything is exact. We don't have to do approximations because it's the free particle. Here's the mapping. It's more challenging for higher orders, but it can still be done. We haven't used it much yet because it gets pretty complicated. But it doesn't just work at a second order. Now I'll return to second order for now. So now if we do have a potential, usually this moment dynamics is not exact unless it's harmonic or the free particle. But we can use this Taylor expansion as in this definition of the effective Hamiltonian. So we get a new term V double prime times delta Q squared. And then in canonical variables, that's S squared. And for delta P squared, we get the previous PS squared plus C over S squared as in the free particle. So that's now, again, a 5-dimensional system. C is conserved. So if we fix a constant, it's down to a 4-dimensional phase space, QP and SPS for a 2-dimensional classical system. Now applications to tunneling, V double prime around a local maximum is always negative. So the S squared term lowers the potential. So if you move a little bit in the S direction, if we increase quantum fluctuations, the potential decreases. So if you do that around the maximum of a potential, the effective potential decreases. So there's a way for trajectories to move around it in this QS space. So you move around the classical barrier. So with this method, that's been used in quantum chemistry, for instance, one can describe quantum tunneling just by classical trajectories with conserved energies, because in this extended space, the maximum can be bypassed. So that's an example. It's a cubic potential. So classically, it would just be the contour here at the front. And then in the S direction, it's extended by this Taylor expansion. As we can see here, the contours. So here we have the classical barrier, but it decreases in the S direction. So we start somewhere around here. There's a minimum, sufficient amount of energy. It doesn't have to be above the barrier energy, but has to be enough to move around the saddle point here. And then there's a way, again, conserved energy to move around the classical barrier. So that means physically, if there's a wave function, S has to increase, so it has to spread out or split up into two wave packets on two sides of the barrier. And that's just described by the single variable S here. Here's a more quantitative example, also a cubic potential. And so there's an exact solution numerically, so just evolving a wave function at a certain, starting at a certain initial expectation value, letting it move toward the barrier, and then figuring out when the expectation value reaches the other side at the given energy. So in quantum mechanics then, or that determines the tunneling time, which is plotted here. So in quantum mechanics, that's always finite. And just has a maximum somewhere, depending on the starting position. Classically, the tunneling time goes to infinity if we get close to the to one side of the barrier. And then the second order mapping, which I showed on the previous plot, also has a range where it's infinite. It does get closer to the full result than just classical evolution, but doesn't completely describe tunneling. But if we include third order, so with this extended moment description, then the blue curve is much closer to the quantum evolution and has finite tunneling times for all initial positions. So that's quantum mechanics, tunneling effect in one dimension. Now, I mentioned non-locality. So in this quantum mechanics, turns out there's some non-adiabatic approximations. And we can first see that here if we go back to our Taylor expansion. And the usual assumption in derivative expansions in particle physics implies that quantum fluctuations or moments evolve much more slowly than expectation values. We can implement this from this starting point here as well. If we find a minimum just in the S dependence, so just the last two terms at fixed Q, and if we are near the minimum of this S dependence, then S doesn't change much. So that's an example of this adiabatic behavior. If we minimize these terms, we get this expression for the minimum, and then plug back into these two expressions, and we get this simplified adiabatic effective potential. And that's exactly what's been calculated here as an example of standard low energy effective actions in quantum field theory. So we get the same square root of V double prime. So here it appears only as a special case. So only if we minimize the S dependence that we have this equivalence. But in general, if S is a free parameter, an independent variable, as in these tunneling models, then it's a more general description. So it includes non-adiabatic dynamics if S is not close to its minimum. This can be done in field theory as well. So this would be, the analog here would be the Coleman-Weinberg potential for a scalar field. And using moments for fields, so for Fourier modes, basically, it's possible to derive this effective potential, again, using these Taylor expansions and the moment description. It looks very different, but it turns out the K0, so the time component of the K integration here, can be done explicitly in Coleman-Weinberg potential, and it implies the same potential that can be derived from the moments. And so here we have the same kind of square root. There's an extra K square term if there are field modes. But if K is small, so in the infrared, we just return to our low energy quantum mechanics effective potential. And that's usually a problem. The infrared problems, if V double prime is 0, we get a root-like pole. And in field theories, for a scalar field, that would be a massive scalar. So that's exactly when we run into infrared problems. But that's only implied by this adiabatic approximation. So the full potential on the previous page. Well, we're not, I mean, it's not manifestly Lorentz invariant, but it's the same potential just with the K0 integration done explicitly. It doesn't violate, it's just, it's not obvious, but it's still there. Well, we're still integrating our spatial Ks as well. We just did the K0 integration explicitly, and we leave the spatial K integration. Oh, in the cutoff, yeah. That's right. Yeah, I'm not really using it very much. I just want to draw an analogy here with the infrared problem, which is which can be seen even without Lorentz invariance. Yeah, I wouldn't even advocate making this cutoff because it's easier usually to just keep using this S dependence, and then we don't get any square root. So we don't get into any infrared issues. A little more generally here, so we had this minimization condition on the S dependence, which through Hamilton's equations means PS doesn't change much. So that's this adiabatic condition. One can do this more systematically, going to higher orders in an adiabatic expansion, and then we get a whole series in higher time derivatives. So that's how this connection to derivative expansions appears. But it's usually very tricky. So first of all, on the previous slide, we had these infrared issues at 0th order. And if we really want to stick with the derivative expansion, it's non-local in time. We have to, we get huge orders of derivatives, or all of them, if we don't want to make any approximation. And both problems are solved if we just keep S, or analogous variables in with their moment for fields, as an independent variable. And that's what I mean by quasi-classical formulation. So it can address non-local and non-adiabatic properties. Now, from the point of view of non-local field theories, S is what would be called an auxiliary variable. So in many cases, if you start with a non-local field theory, you can introduce auxiliary variables and make it look local. That's basically what's happening here, except that S is really a physical degree of freedom. It's the variance of the wave function. Here's a simple example. So if we have this kind of non-local action, then it can be made local by introducing this auxiliary field psi and a Lagrange multiplier lambda. So integrating over lambda implies that any differential equation for psi, which is solved by what appears here in the square. So these are equivalent actions, even though one of them is non-local, one of them is local. So in terms of Poisson structure, the auxiliary field psi here is like the S variable. A lambda, Lagrange multiplier, has vanishing Poisson brackets with anything else. So that's like the C in the uncertainty relation. And so that's the formal analogy. But again, both C and C have meaning, physical meaning in this moment description. And then in some cases, it might be possible to completely solve for S of Q without using adiabatic approximations. And if we then stick that S of Q into the original mechanical action or Hamiltonian, it's going to be non-local. Now, an application, so cosmology here, it's a model of Higgs inflation. And initially, the idea a long time ago was to use the Higgs field as an inflaton field. So it would be very nice because we wouldn't need an extra scalar field. So we would know the potential. The problem is the renormalizable potential is not consistent with observations. So that's why it wasn't used. More recently, then people noticed if there's non-minimal coupling to gravity, can still work, but again, requires an additional ingredient through non-minimal coupling. Now, in the next few slides, I show that non-adiabatic behavior can actually also make it consistent with observations. In this case, because it's a 4th order potential, we have to go up to 4th order terms. And I won't use the full mapping from before, because it introduces too many degrees of freedom. But instead use a partial truncation. So it's not truncated fully to second order as the other quantum mechanics models, but we still use the relationship between fluctuations of the inflaton field and some other field phi here instead of S. And then we include third and fourth order moments by parametrization. So we assume that delta psi cubed, so a third order moment is a constant, some parameter alpha 3. And the fourth order moment is proportional to phi to the fourth, so that works out with the units of the field, with another coefficient alpha 4 here. So in this case, we only introduce one additional degree of freedom, one additional scalar field phi. And so we get a two-field inflaton model from this initial single field Higgs potential. The parameters can be interpreted as non-Gaussianity. It's non-Gaussianity of the background. We haven't introduced any perturbations in homogeneity at this point. But the Gaussian would be a special case in which alpha 3 is 0 and alpha 4 is equal to 4. So differences from these values are non-Gaussianity parameters in the background state. Now, the Taylor expansion gives us this full potential, so up to fourth order in both psi and phi. And then we get the C over phi squared term as before from the kinetic energy. The Klein-Gordon potential, or full Hamiltonian, on curved spacetime has different metric dependencies in the potential and the kinetic energy. So we get an extra metric dependence here, which is through the scale factor. So that's only in the term that comes from the kinetic energy. Now, this potential is nearly flat around the critical value of phi. So when this difference here vanishes, so V was a parameter in the original Higgs potential. And so we'll analyze this a little bit. And the new C over phi squared term is repulsive at small phi, again, because the uncertainty relation has to prevent phi from getting too small. So if we look at this small phi behavior and the large phi behavior in the last term here, again, there's a local minimum given by this value here. And if we want to avoid the Transplanckian problem, we have to assume that this initial volume here is sufficiently large, greater than the Planck volume. So the initial value is bounded from below. So the initial value, which is in the region allowed by this 1 over phi squared and phi to the fourth potentials. Now, if V is greater than M, which is the case in most Higgs models, then this initial value, at least the maximum, is greater than the critical value of this quadratic term, which I copied again up here. So initially, we have a standard parabola for psi. Now, the repulsive potential initially prevented phi from being too small, so it pushes it up over the critical value. But as the universe expands, A increases, so the repulsive potential decreases, which makes it possible for phi to decrease and fall below the critical value at some point. And the transition is shown here. So initially, parabola, so psi will just oscillate. But near the critical value, the potential for psi is very flat. And at some point, it turns into a tachyonic contribution around 0 psi. And then it goes, it's still bounded because it goes into the psi to the fourth branch at some point. But somewhere in this region, in this flat behavior, and then what's called a waterfall regime in hybrid models, when it opens up and makes it possible for psi to move to a new minimum, somewhere around there, the potential is sufficiently small to allow for slow roll. Here's some evolutions. So as instead of time, the number of e-foldings is plotted here. We have the value of phi. So that's the second field, so the fluctuation field. It comes down from this initial large value greater than the critical energy, the critical value of phi. And then it approaches its a new minimum and then just follows that minimum. Psi is shown here. So it starts around the minimum of this psi potential here. And then it starts increasing very slowly as this parabola opens up and then moves into this waterfall regime where psi starts changing very quickly. And this slow roll regime here is, in this case, valid for just the right amount, just a little more than 60 e-foldings. And we didn't really have to play with initial values. It was easy to find these evolutions. So a slow roll and adiabatic in a very long range of time. But the initial stage, so setting up the right initial values and then exiting from inflation, are very non-adiabatic, so very fast changes, which require this two-field extension. And so then in quantum mechanics, non-adiabatic dynamics of the fluctuations. A few more results here. So that's, again, number of e-foldings and the spectral index, so also in the right range. And here it's, again, number of e-foldings, and then there's alpha 3, so one of the non-Gaussianity parameters for cubic order moments. So we can estimate what kind of non-Gaussianity we need. It can't be 0, turns out. So we need some non-Gaussian initial state. And more details, structure formation, give us this approximate relationship between the number of e-foldings and the spectral index. F is some pretty complicated function, but it has only logarithmic dependence on 1 minus ns, so it doesn't contribute too much. Now, comparing this with non-minimal Higgs inflation, in this case, F would just be equal to 2. So, but it has the same 1 over 1 minus ns behavior, which is what makes it consistent with observations. So this formula is very close, but in this case, there are no non-standard ingredients like non-minimal coupling. So it's really just quantum mechanics applied to the Higgs field and including these non-adiabatic terms. Now, a few additional applications. I won't spend too much time on each of them. Here's a mapping for 2 degrees of freedom. So again, usually it's a tricky problem coming up with canonical coordinates. For 2 degrees of freedom, second order moments, there are 10 independent moments. So there are 3 for each of the 2 pairs, and then there are 4 cross moments, cross correlations. So it's a 10-dimensional phase space, and it's parameterized by 4 canonical pairs. So that adds up to 8 variables and 2 of these Casimir functions. And that's a parameterization that works. So S1 and S2, 2 of the new configuration variables are, again, just individual fluctuations. There's a new variable beta, so that's one of the canonical variables which determines correlations, just like an angle, which is the cosine here. And momenta appear in some of these covariances. And then there's a 4th parameter alpha with a momentum p alpha, which completes the canonical pairs. And then U1 here is one of the Casimir variables, and there's second U2, which I didn't write down here. So the equation where it gets more complicated is delta P1 squared. So initially it looks like what we had before, but now U1, actually U1 is not a Casimir. I think I just said it is a Casimir, but it's really this complicated phase space function, and C1 and C2 are the Casimirs. So U1 or delta P1 squared has a pretty complicated dependence on the momenta even, which is not quadratic, non-polynomial. So it's a pretty complicated effective Hamiltonian. But at least numerically it can be used. So one example is a back reaction effect. So we interpreted one of the classical variables as a background, just evolving linearly. It could be a cosmological model as well. And then there's a second dynamical variable which is evolving on this background and back reacting. And so there was this delta Q1, Q2 term. So quantum correlations between these 2 variables, if they are switched on by including this term in an effective Hamiltonian, it can pretty drastically change the behavior. So the blue line is just for a single degree of freedom. So that means ignoring quantum correlations. So in this case, it's just a damped oscillation. If both degrees of freedom are included with quantum effects, so that means introducing these correlation terms, then there's a beat-like phenomenon. So the amplitude doesn't decrease uniformly. There are additional oscillations in this case, which in cosmology might have an effect on particle creation, for instance. Now, as an example of non-local effects, so that requires quantum field theory. So if it's not quantum field theory, that would just be non-adiabatic. But the question that we addressed here was a question that's been raised a few times. Inflation is supposed to predict how inhomogeneity, how structure can emerge from a vacuum state. But the vacuum state is translation invariant, so it doesn't have any structure. So how can the structure appear? And the approach here was we refer to the BKL scenario. So there's this scenario which tells us that if we are close to a space-like singularity, then locally the dynamics looks exactly like a homogeneous model without spatial structure. But on a certain length scale in space, it has to be inhomogeneous. So in cosmology and inflationary cosmology, that would usually be considered super-horizon inhomogeneity. So inflation initially happened just in a very small spatial region. So it wasn't sensitive to what this near singularity structure should predict. And then in local dynamics, super-horizon inhomogeneity can't back-react on sub-horizon inhomogeneity. So it's usually ignored. But non-local dynamics could imply back-reaction effects, interactions between super-horizon scales and sub-horizon scales. And so we try to show that that's at least possible. We haven't formulated a quantitative model yet, but it turns out it is possible. So to set this up, we again started with two fields. One of them in this case was just a background field, which is nearly constant, but then has some large-scale inhomogeneity for these super-horizon scales. And then there's a matter or an inflaton field psi, in this case without any specific potential, but with inhomogeneity. So it has Fourier modes, and then certain moments in which these Fourier mode operators appear. And for the background, we didn't include Fourier modes except for one that determines large-scale inhomogeneity. So K0 is small. And now, don't have a lot of time left. Given this quasi-classical description, we can again run through our effective Hamiltonian, do a Taylor expansion, which now includes infinitely many variables for all the modes. And but we know at least a certain number of modes have to appear, because if there are interaction terms between this psi field and the background, then there is a potential, an effective potential term, which includes this moment. So some interaction term between a k moment and a k plus k0 moment. K0 is small, so these are nearby wave numbers. And then, so there are a few equations here. We don't have to look at all of them, but one can go through moments that get non-zero time derivatives from this term in an effective potential. One of them is this one here. So this one starts growing, which wasn't non-zero initially. And then that moment appears in a Poisson bracket with something from the kinetic energy of a quantum field and the original moment that we started with here. So that moment also has a non-zero time derivative and has to start growing. And going through a few more equations of motion like this, we can show that also a 2k0 displacement has to grow. So we're increasing the wave number difference from k0 to 2k0, and this can be iterated. So we can just follow the same set of equations. So we are generating non-zero moments between k modes and k plus any integer times k0. So this initial k0, which was small, is translated into a very large integer times k0 after many steps. And in this way, the initial large-scale inhomogeneity, so small k0, is translated to small-scale inhomogeneity with large n times k0. So this shows that it is possible in this description. So it's a local formulation of non-local dynamics it is possible for superhorizon inhomogeneity to imply subhorizon inhomogeneity after some time. It really takes a long time because we have to go through many iterations here. So each iteration implies that one of the moments starts growing. So it takes a long time before one of these large-scale moments really, or large number times K0 moments starts getting non-zero, but eventually it will happen. So it's a complicated set of equations, so we have to run some numerics, which we haven't done yet, but at least it's possible. A final example, application to gravity. So far, everything was fields on some curved backgrounds, but no quantized gravity. And I'll just sketch how that would be done in principle. So that's also an open problem. Since it's Poisson geometry canonical, we would use a canonical description of gravity. So instead of using coordinate transformations, we use hypersurface deformations as the equivalent description of gauge invariance. And the corresponding brackets are of this form. So these could be Poisson brackets in classical canonical gravity or commutators if it's quantized. And famously, there's a structure function. So the coefficients on the right depend on the metric. And the metric itself is supposed to be quantized. So that's what making canonical gravity complicated. But now in this quasi-classical description, we will try to turn these expressions into effective terms like these Taylor expansions. And I'm just showing here a few examples in spherical symmetry just to get an idea of what these expressions look like. So these are non-polynomial, so it would be more complicated effective constraints. So effective versions of S and T. And then we would define effective constraints just like the effective Hamiltonian. So expectation values define functions on state space. They would have to be zero, so they look like classical constraints. But for quantum operators, if we multiply an expression like T and S by some other operators, usually expectation values change. So these are expressions like these with F and G could be polynomials of E and K, are additional independent constraints. So we don't just get an infinite dimensional phase space, we also get an infinite set of constraints, which again has to be truncated. And we're still working on the details, but it's at least in these spherically symmetric models with this type of constraints, it is tractable in some cases. And so that's that would be a way to include gravity really in a quantized form in these quasi-classical descriptions and then have non-local gravitational effects. So to conclude, so the main common theme here is really mathematical. It's this Poisson geometry, which unified many other approaches as we saw quantum field theory, quantum chaos, quantum chemistry, quantum cosmology. And it's, of course, not always suitable, but in many cases, it's more efficient than working with wave functions. It's also more intuitive because we can use effective potentials. And it allows us to include non-adiabatic and non-local quantum effects. Something that I didn't have time to talk about is new quantum effects in chaos in cosmological models as well. Now, detailed cosmological models, black hole models, so that would require quantization of space-time as well, which just briefly mentioned is still in progress. But in this case also, it seems that this formalism can be applied. It requires more detailed discussions of covariance. So with moment terms, fluctuation terms, somehow we still have to be able to do coordinate transformations, and that's usually a tricky issue. But this can be shown in some cases. And then final application here, I just mentioned this because we're still looking for interesting versions in cosmology. The definition of moments only requires an algebra. It doesn't require wave functions or Hilbert spaces, so it can be applied to non-associative quantum mechanics as well. So that would be another generalization. And so far, the main application has been in for magnetic monopoles. It can be used to derive new upper bounds on possible charges. String theory for some time was interested in non-associative structures. It's gone down a little bit, but somewhere in this area, there might be connections to cosmology too. So I'll stop here. Thank you for your attention.
Okay, questions?
Thank you for your talk. I'm a little bit surprised because we know in the case of the effective potential for the Higgs field, how is the effective potential at k equals 0? So it contains logarithmic terms and things like that. So why don't you have those terms in your approach? Why is your, basically totally different from what we know in standard case? And
Yeah, these are renormalization terms. So that would be implied if we included back reaction from moments or field moments of the psi field, which we haven't done. So we are really just quantizing the background field at this point using these quasi-classical methods.
so how do you call, what do we call it effective potential? Then, you should be able to get this log term.
We
eventually.
should be able
Otherwise,
to-
otherwise that's not, it's difficult for me that I come from quantum field theory to think as an effective potential, that thing, no? You see
Yeah,
my problem.
We would get the log terms like this one here. We would get them if we included field theory moments of the Higgs field, which we haven't done yet. They would also be there. We just haven't included them. But on top of those, there are these additional terms which are not included in low energy effective actions because they can't be shown in a derivative expansion. So that's what these new terms are. So these are non-adiabatic terms, which are just, if you do a low energy effective actions, you just don't get them. So we're including those. We ignore those others because they are well understood. And it turns out these new terms also have additional effects.
Yes.
Marta, thank you for your talk. And you mentioned about the quantum to classical transition, right, of perturbations. And but I didn't understand how because you mentioned that the vacuum state is homogeneous and continues to be homogeneous, and but how it happens in your approach.
Yeah, it's not exactly quantum to classical. It's really it's homogeneity to inhomogeneity, both on the quantum level. So there would still have to be some additional transition, inflation or decoherence, to turn that inhomogeneous quantum state into a classical distribution. But even on the quantum level, people have questioned how it's possible for a translation invariant vacuum state to produce inhomogeneity if it's translation invariant. So that's what we're trying to address only at the quantum level.
Okay, another question? Okay, so we have well, thank you again. We have a slight change in our program. Now I would like to invite Professor Hugo Mosquela to present us a piano piece called Quantum Cosmos. And coffee break is afterwards. So, presentation. But so should we say before coffee?
Presentation with music.
Yeah, that one. That I just.
I would say they did it now and then.
Yeah.
That's what is my presentation.
so since we have a little time before we start, let me tell you something about this piano. This used to be a piano. It's no more a piano. Now it's I don't know what. Because a piano lives 100 years. It's well paid. It's not it's well. This piano has died sometimes ago, but it used to be a noble piano. It's a Pleyel. Pleyel was the piano of Chopin. So it has a beautiful sound, but it's completely out of tune. Let me tell you, it's completely out of tune. But also, there are portions, because a piano suffers an enormous tension, tones of tension, so it cannot survive as a violin, which are no problem at this time. So if we are this also, it's completely dead, down to the break, harmonic stable, so it's broken. So, but the sound is beautiful. So Arturo Benedetti Michelangelo would have never played such a piano, but not. Alfred Cortot, on the other side, would have played also on a piano with broken keys. So I think that the side of Alfred Cortot, and even the side of Claudio Arrau, the Chilean pianist, who used to play also without a piano. He went once for a concert in Argentina somewhere, in the end of Argentina, and there was no piano. So that was a limiting case. So this was a piano, now it's no more, but I do this final note. Conference because Mario asked to do it, and I always do what Mario asked. Let me wait for, so it's part of the workshop. It's a talk concerning 1, 2, and 5. And there is some I can't really start playing the first introduction or something like that. Let's start with the first. But it's not, but it's not. Flavia. So this is under Claravanda, which is not ethical. That's your weak monster. This is a melody without a melody. I don't know if you appreciate the fact that there is no melody in here, just harmony. Okay. You may think that there is a melody, but there is no. It's just in the same way as in this prelude of Bach. There's no melody, but you get the melody. This is harmony. Harmony has the same source, the same origin as cosmology, and indeed as quantum. Sorry about this. I didn't say that I should post my presentation, but that's not. So there is a man which is at the origin of cosmology, and indeed of quantum cosmology, and indeed of harmony. And this man is Pythagoras. Pythagoras is a philosopher who lived in the 5th century before Jesus Christ, in Calabria, which is the same land where Professor Mario Novello comes from. It's better. Much. Little bit of too much, no? There is a back reaction here. Perturbation. So maybe you don't know, or either you know, if you don't know, I'll tell you, the name of the universe as a whole did not exist ever. It was introduced at a certain point of the history traditionally by Pythagoras. Pythagoras was this philosopher. Maybe you heard the name of Pythagoras in your youth when you were learning about Pythagoras' theorem. But Pythagoras also is the one who is said have invented the word to design the totality as a whole. And this word is cosmos. Cosmos meant a necklace for human, and they use the cosmological usage took century to take place.
Okay. So Pythagoras didn't write anything, and the first Pythagorean who wrote things in which we have memory, written memory of him, even by Plato, is Philolaus. Philolaus is, but I should wait for my transparencies. So Pythagoras discovered essentially everything, says Bertrand Russell. He discovered, did you get it? Have you got it? I sent you by mail. A WeTransfer link I sent to you. You got it from by WeTransfer. Okay, I will do without the presentation. So you can take it out this, I will write on the blood for you. Io continuo così, tanto dura pochi minuti. So let me, can you take out this? I will write on the platform. What has happened? Volete andare per il coffee break che facciamo dopo? Okay, let's wait for the file. Sorry about this. Right. So this is supposed to be a divertissement, but not a divagation, in the sense that it is in the terms of what we are supposed to discuss here, quantum and cosmology. This is the thing. So these are the two guys which were related to the place I just played. I replayed just the first section. And pay attention that there is no melody. So you know these two persons. This is Newton and this is Handel. They lived together at the same epoch. Newton was a little bit older than Handel, in London, in England. And indeed, they are graved in the same place, Westminster Abbey. They met several times during their lives. And Newton used to say that when he saw Handel play, the only thing he impressed him was the elasticity of his fingers. So that let you understand how bad was Newton. So another curiosity here is the date of the birth of Handel. Handel was born in 1685 as Bach and as Scarlatti. And here you see it is February 1684, because at that time in England, New Year started from March 25, which is the conception of Christ, not the birth. Okay, so the new year, it was at March 25. So this is not a mistake. It's old England way of counting the dates. So this is harmony. Okay, this is just harmony. Is, by the way, harmony and say polyphony is the true novelty of Western European culture. Everything else was invented by the Greek. So this is the father of everything, which is Pythagoras, and I put here one Portuguese Brazilian version of his life written by Porfirio. This is Pythagoras, this is Porfirio. And Pythagoras is the one who named the cosmos. He named the cosmos, and naming the cosmos. So this is this is again Pythagoras, and this is the other character of our little talk, Philolao. This is a middle-age xylography of Philolao, and you see they are playing instruments. Philolao and Pythagoras, of course, is an anachronism because Philolao was born after the death of Pythagoras. And here is the thing I was mentioning to you before. This is a quote from Ezio. Pythagoras was the first to call cosmos the compassing of all things because of the order that reigns in it. This question of the cosmos means beauty that comes out of order. So it's already a cosmology. The cosmos is not a chaos, it's something which is ordered, and the order is expressed by numbers. This is the idea, Pythagoras, Pythagorean, and what we found in the writings of Philolaus and in the quote of Philolaus by Aristotle and Plato. And here is the quantum. You see, this is the mythical event when Pythagoras was passing through some place where there were people hammering something, and so there were several tones. So he understood there was something going on. So Pythagoras invented the monochord, and the monochord is the first quantitative law in physics. So Pythagoras understood that if you play with the chord one note, and then you divide the chord by 2, this is the note that will be the outcome of that. If you divide the chord by 3, you get this one. If you divide the chord by 4, you get again a do and a mi. So this is the first quantitative law in physics. Indeed, it is the first quantitative law in science. Okay, and it was so striking, this fact for them, that they believed to have found not one law but the law of nature. So this structure, this quantum structure of the monochord, which produces several notes depending of the vibrating modes, the possible vibrating modes, is a discovery of Pythagoras, let's say, which founds harmony, because, as I will explain a little bit later, but there was some discrepancy here. This is the comma Pythagorean. I don't know if you ever heard about this thing. This means that if you, so you see, you produce this note, then this note, then this note. So the first interval that you produce is the 5th, do, sol. Okay, but there is a problem. If you go doing octaves, or you go by fifths, at a certain point you get to the same place here, but not exactly at the same place. This is because power of 2 and power of 3 are not commensurable. So there was an irrational number there, and this was sort of a crisis, which in some sense caused the secret society of Pythagoras. This was a secret not to be revealed to anyone. You see, that's the esotericism of Pythagorean was also to protect this secret. Okay, so here is Pythagoras with his own monochord, making experience about quantum quantization of the modes of a string, let's say. So it was a string theorist, Pythagoras. And here is the tetractys. You see, this is the magic number of Pythagoras, is 10, and it is so holy that you see the tetractys is this triangle contains exactly 10 triangles and 10 points. You see that there are 10 triangles, 9 little triangles and 1 big one. And the sum of 1 plus 2 plus 3 plus 4 is 10. Okay, this 10 is a holy number for Pythagoras. And this, the ratios of this thing give this interval, and this interval. So the 5th, the 4th, and the octave were the interval. And with this interval, Pythagoras produced is scale. Okay, so it is an outcome of this quantization. So why this? Now I will going to tell you something that may surprise you. This is the I don't know if you ever read the first pages of Copernicus book. Copernicus book is talking about who else before him was looking for a moving Earth, and the names Philolaus and Icetas di Siracusa. This is the model, the cosmological model of Philolaus. You see, Philolaus suppose that the center of the universe, Philolaus is the first, by the way, of putting the correct order of the planets. Okay, so is the first to do this, and he put in the center of the, let's say, universe. By the way, Philolaus is also the first to have introduced the idea of an infinite universe, well before Giordano Bruno, because for Philolaus, the universe was made by limited and delimited and the unlimited. Okay, and harmony was taking together the limited and the unlimited. So harmony is something putting together things which are different. This is the idea of harmony by Philolaus. So you see, this is the Philolaus system. The Earth is rotating around the center, which is occupied by a fire. It's called Hestia. There is the anti-Earth also. Anticton means the second Earth, which we cannot see because the Earth always we are on this side of the Earth, never can see this one. Okay, and the Earth is put in movement around this center. We don't see the anti-Earth. So Aristotle itself, this model is predates the geocentric model. Aristotle itself asked himself why Philolaus did this, and also why Philolaus introduced an anti-Earth. And there are several hypotheses. The most common hypothesis is that since 10 is the magic number, we need 10 planets going around. But if you count also the fixed star, it makes 11 and not 10. But then there is a very interesting, to me, musical hypothesis. And the musical hypothesis is this. This is the ancient classical lyra, which you see as 7 chords. 7 chords, which is also a holy number. 7 chords correspond to the 7 planets. So the 7 planets make the sound of the sphere that only the initiated belongers to the Pythagorean school could hear, you see. But then there was a technological improvement, and the lyra got to 9 chords. So 9 chords, and the 9 chords had to be in correspondence with the planets. So the movement of the planets, because if the Earth is static at the center of the universe, it does not produce any sound. So the music of the sphere requires movements of the sphere. So the Earth has to be put in movement. So this is a heterogenesis of the scopes. Of course, also the introduction of the cosmological constant by Einstein was for a reason which is not good at all today. But there are several roads to the truth, and the idea of the movement of the Earth as a musical route. So quantum cosmology and music go together in the thinking of Philolaus. Here I represented the different scales, and this guy who coded the scales with the name of the planets associated to the notes is Pliny the Ancient, Plinio il Vecchio, which is a person who lived in the town where I come from, Como, in Italy, and this year is 2000 years from his birth. So then in the work of Keplero, since the orbit were elliptical and no more circular, every planet has his own melody, let's say, small or big, depending on their eccentricity. Okay, so this was just the first thing I wanted to convey to you. There is a common source to cosmology, quantum, and the music in the works of the Pythagorean school. And I'm not the only one to admire this thing. Bertrand Russell says that everything is already contained in the ideas of Pythagoras and Plato and Aristotle. They do develop his ideas. The second thing, it concerns time, and then this will allow me to play the second part of my musical program. So you may not recognize in this thing, and is in this thing, clocks, because we are talking about quantum cosmology, but the mystery of time is not really addressed by quantum cosmology. If we think about the standard idea of quantizing gravity by quantizing the three-dimensional part of the metric, okay? Wave function of the three-dimensional part of the metric. So time remains a mystery, but the very first talk here was about time, as you remember. Someone told us that the only thing we need to measure is time. And indeed, time is the oldest thing we measured. This is a clay tablet of the Babylonian time, 2000 years before Christ. And in this tablet, there are calculations similar to calculation of Donato's, because there are many numbers. They were computed by Maples, it seems. It quotes the time of the night guards, and this time was measured by water clocks. Water clock is the oldest physical measure that has been done. Before measuring lengths, they were measuring time intervals using water clocks. Not only, so this is an old piece of an Egyptian water clock, 2000 years before Jesus Christ. This is a Chinese water clock by Sun. So this is very complicated. It could be a Patek Philippe of the water clocks. And now I'm going to play two preludes of Chopin, because this is a playel, which are called the rain water drops, and they are related to gravity in at least two ways to my view, because these two preludes are I cannot use this anymore. These two preludes are called the water drops. There are two of them in the collection of preludes. The devil is here. So you see, this is the first prelude. It was played at Chopin's funerals. The water drop here is in the higher I register. You see this drop here. And in the second prelude, the drop is down. And you will feel the drop in the low register. But these two preludes are tragic, indeed, both of them speak about the death, and in this sense, they are also grave. So there is some sort of ineluctability in those preludes, which is the in a way also also something which attracts without the possibility of escaping. So let me play to you these two preludes of Chopin, which are called the water drops. This was played at Turin and Chopin's funeral. These two preludes were composed in Palma de Mallorca when Chopin was trying to get rid of tuberculosis. And in Palma de Mallorca, George Sand made the transportation of piano identical to this one. A player from Paris for sent Palma de Mallorca. Identical.
Mm.